Myself Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So in this particular lecture, we are going to learn about definitions and different terminology we will learn in this particular module 3, that is uniform plane wave characteristics in electromagnetic waves and the transmission lines. Define uniform plane waves. What do you mean by plane wave? How are we going to define about uniform plane waves? So an electromagnetic wave originates from a point in free space and spread out uniformly in all directions, and it forms a spherical wave called uniform plane wave. So an electromagnetic wave which is originates from a point in free space spread out uniformly means in all the directions it will be spreading in equal directions, and it is forms a spherical wave. Then it is said to be uniform plane wave. Uniform plane wave is a wave that will have the direction of components will be uniformly distributed in all the directions, right? So in order to define this, we must consider first free space medium, right? So definition for uniform plane wave means an electromagnetic wave originates from a point in free space and spread out uniformly in all the directions, and it can able to form a spherical wave. Then is define skin depth. So to define this skin depth, we need to consider two types of the materials, as insulating material is called as dielectric material and another one is conducting material. So where the skin depth is defined based upon the conducting materials or conductors. So the skin depth is a measure of the depth to which an electromagnetic wave can penetrate into the medium. The penetration means inserting into the medium. So the skin depth is a measure of the depth to which the electromagnetic wave can be penetrate into the medium is defined as the skin depth, and it is represented with delta, that is given by 1 by pi f mu sigma under rho. So depending upon this, skin depth delta is inversely proportional to the square root of frequency and conductivity of the medium, right? So in order to define the skin depth or depth of penetration, the skin depth is the depth at which the electromagnetic wave penetrate into the medium is called as skin depth or depth of penetration, and it is denoted with delta, that is given by 1 by root of pi f mu sigma. Next is define oblique incidence. So when a uniform plane wave incidences obliquely with some angle other than that of 90 degrees, to the boundary between the two medium, and it is known as oblique incidence. Normally, incidences are occur in two different cases. One is normal incidence and another one is oblique incidence. So when a uniform plane wave incidences normally, then it is normally between the boundary between two medium, then it is said to be normal incidence. Now coming to the oblique incidence, when a uniform plane wave incidences obliquely with some angle other than that of 90 degrees, less than that of or greater than that of 90 degrees case to the boundary between the two medium, then it is known as oblique incidence. Objection must be there or obligation must be there between two boundary or between two media. So oblique incidence. So depending upon this uniform plane wave is the wave that will have the variation only in the direction of the wave, how the wave is to be propagating, and the rest of the fields are to be considered as constants. Means an electromagnetic wave originates from a point in free space spread out uniformly in all directions, and it forms a spherical wave. Then in order to define the skin depth, we need to consider conductors or conducting materials. So depending upon this, the skin depth or depth of penetration can be defined as it is the depth at which the electromagnetic wave is penetrating into the medium is called skin depth or depth of penetration. Depending upon the incidences occurs the second type of incidence called oblique incidence. And when a uniform plane wave incidences obliquely, means the angle there we have considered is other than that of 90 degrees case and the boundary between two medium, and it is known as oblique incidence. Then, what is transmission coefficient of electromagnetic wave in a medium? The transmission coefficient is defined as the ratio of the magnitude of transmitted field to the incident field. Generally, it is represented with tau and it is given by Et to the Ei. Generally, when the incident wave incidences in the boundary, part of the incident wave is reflected back to the same medium, and part of the incident wave is transmitted to the next medium. Depending upon that, we will define two types of coefficients as a transmission coefficient and another one is reflection coefficient. Now here, transmission coefficient means it is the ratio of the magnitudes of transmitted wave electric field strength to the incident wave electric field strength, and it is given by tau equal to Et by Ei. Right? Similarly, reflection coefficient means it is the ratio of the reflected wave field strength to the incident wave field strength. Depending upon the medium, we will depending upon this uniform plane waves, we will define two types of coefficients in a electromagnetic wave as transmission coefficient and reflection coefficient. Next, what is plane of incidence? Then plane of incidence. A plane which contains incident ray and normal to the boundary between two media is known as plane of incidence. Basically, it consisting of what it contains. Plane of incidence contains incident ray or incident wave, and it is normal to the boundary between the two media. That it is called as plane of incidence or normal incidence. There are two types of incidences occur, and depending upon the incident wave touches or strikes the boundary, that is normal incidence and oblique incidence. When the incident wave touches the boundary normal to the boundary normally, then it is known as normal incidence. When it is touches obliquely, means the angle is less than that of 90 degrees case, then the type of incident is said to be oblique incidence. Next, describe linear polarization. So, linear polarization is accomplished when the electric field vector possesses only one component or two orthogonal linear components that are in the time phase. Suppose if you have the field component Ex and Ey, if the linear polarization is accomplished when the electric field vector or orientation of electric field vector we consider only one particular direction or two orthogonal linear components that are in phase. Means the angle between two x and y components becomes zero case, it is said to be linear polarization. Depending upon how the electric field is rotated into the medium, depending upon that, there are three cases of polarizations occur: linear polarization, elliptical polarization, and circular polarization. Now here, linear polarization case, if you have the component is along x and y component becomes 0, then it is said to be linearly polarized in x direction. Suppose instead of getting x component, if you have y component and x component becomes 0, then that is the case wave is said to be linearly polarized in x direction. Okay, so transmission coefficient of electromagnetic wave means, now to define this, we need to know the magnitudes of transmitted wave as well as the incident wave. So it is the ratio of transmitted wave field strength to the incident wave field strength, and it is given by tau, which is equal to Et by Ei. Then to define this plane of incidence which contains incident wave and normal to the boundary between two media, then those are said to be plane of incidence. Then coming to the polarizations case, here we will define linear polarization. Means in linear polarization, it is accomplished or formed when the electric field vector possesses only one component or two orthogonal linear components that are in phase. Orthogonal components means the two are connected in, means the angle between two will be is exactly equal to 90 degrees. Next, define intrinsic impedance or characteristic impedance. So it is the ratio of electric field to the magnetic field, or it is the ratio of square root of permeability to permittivity of the medium. So intrinsic impedance is generally given as represented with eta, and it is given by E to H. It is the ratio of the electric field strength to the magnetic field strength, means it is the ratio of electric field strength to the magnetic field strength, or it is also defined as square root of mu by epsilon. Right? Permeability to the permittivity of the medium. So suppose if we consider the medium to be a free space medium, we are representing it with mu naught and epsilon naught. We substitute mu naught by 4 pi into 10 power minus 7 and epsilon naught by 8.854 into 10 power minus 12. Then the eta naught becomes 120 pi or 377 ohms. Okay, so intrinsic impedance or characteristic impedance can be defined as it is the ratio of the electric field strength to the magnetic field strength, and sometimes it may also defined as the ratio of square root of the permeability to the permittivity of the medium. Suppose if we consider the medium to be a free space medium, then eta naught is equal to root of mu naught by epsilon naught. Now if we substitute mu naught, permeability of free space medium as 4 pi into 10 power minus 7 and epsilon naught as 8.854 into 10 power minus 12, then the approximate value to be obtained for this intrinsic impedance eta naught as 120 pi ohms or 377 ohms. Next is define propagation constant of an electromagnetic wave. Propagation constant means generally we use the notation for that as gamma, and it is the summation of attenuation constant. Attenuation constant is represented with alpha and the phase constant is represented with beta. And propagation constant is always a complex in number, that is plus or minus j. So in general it is given by the propagation constant gamma equal to alpha plus j beta. Alpha be the real term and it is also called as attenuation constant, and beta be the imaginary term. It is said to be phase constant. So the propagation constant constitutes or gives us summation of the attenuation constant alpha and the phase constant beta. So generally it is a complex in number that is given by gamma equal to alpha plus j beta. Next, what is surface impedance? So now to define this surface impedance, it is the ratio of the tangential component of electric field strength to the linear current density Js, which flows due to the electric field. Right? So surface impedance, that is in general we are representing it with impedance means Z, and S stands for surface impedance, which is equal to, it is the ratio of the tangential electric field strength, the tangential component of electric field intensity, that is represented with E tan to the linear current density as Js, which is cause due to the electric fields. Right? So generally it is measured in ohms and it is given by surface impedance, also defined as the ratio of the tangential component of electric field strength to the linear current density Js, which flows due to the electric field intensity in electric fields. So that is represented with Zs, which is given by E tan by Js, and generally it is measured in ohms. Right? Definitions and in uniform plane waves means in this intrinsic impedance or characteristic impedance can be given by here the notation for that as eta, and it is defined as it is the ratio of the electric field strength to the magnetic field strength, or sometimes it may also defined as means square root of permeability to the permittivity, and it is given by eta equal to E by H, which is equal to root of mu naught by epsilon naught. For a free space, for the medium to be considered as a free space medium, and those two, permeability and permittivity, are represented with mu naught and epsilon naught. And if you substitute free space permeability value as 4 pi into 10 power minus 7, and permittivity of the free space medium is represented as 8.854 into 10 power minus 12, then this eta naught, intrinsic impedance of the free space medium, is given by 120 pi ohms or 377 ohms. Then propagation constant of an electromagnetic wave. So in general, this propagation constant is a complex in number, and it gives us the summation of the attenuation constant alpha and the phase constant beta. So gamma constitute alpha and beta, that is gamma equal to alpha plus j beta, where alpha be the nothing but attenuation constant, it is considered to be as a real term, and beta be the phase constant, and it is an imaginary one which is to be called as phase constant. Right? So gamma constitute attenuation constant alpha and the phase constant beta. So gamma equal to alpha plus j beta. Then, to define this surface impedance, what is surface impedance? To define this surface impedance, it is the ratio of the tangential components of electric field intensity E tan to the linear current density Js, which flows due to the electric fields, is said to be surface impedance, and generally it is measured in ohms. Next, define Poynting vector. The vector product of electric field intensity and the magnetic field intensity at a point is a measure of the rate of energy flow per unit area at that point. So generally, Poynting vector means we are considering it as P bar equal to E bar cross H bar. E bar is the rotation for the electric field intensity and H bar be the magnetic field intensity. So it is the multiplication between the electric field intensity vector and the magnetic field intensity vector, which is used to measure the rate of energy flow per unit area at that particular point. Is defined as Poynting vector, that is P bar equal to E bar into H bar. Suppose if we are assuming the propagation vector or Poynting vector in the z direction, means electric field is in the x direction case and the magnetic field is in the y direction case, and the propagation vector or Poynting vector P bar will be propagating in z direction, right? So it is a vector and the product of electric field intensity to the magnetic field intensity at a point is a measure of the rate of energy flow per unit area at that particular point, is said to be Poynting vector. Next is, what is Poynting theorem? From the Poynting vector, we will be defining this Poynting theorem. So the vector product of electric field intensity E and the magnetic field intensity H at any point is a measure of the rate of energy flow per unit area at that particular point, is given by Poynting vector, and the direction of power flow is perpendicular to E and H in the direction of the vector E into H bar. It's given by Poynting theorem. To define this Poynting vector and Poynting theorem, we will be considering two vectors called electric field intensity vector E bar and the magnetic field intensity vector as H bar. Right? So, to define this Poynting vector, first we have to consider it is a vector product and it is given by multiplication of electric field intensity vector E bar and the magnetic field intensity vector H bar. And at a particular point, we need to measure rate of energy flow per unit area in this particular point. Now coming to the Poynting theorem, after defining this Poynting vector, the direction of power flow is perpendicular to the E and H in the direction of P bar. The P bar is Poynting vector. Next, define critical angle. The angle at which incident wave is totally reflected at the interface of two different dielectric media is called as critical angle. Generally, it is denoted with angle is represented with theta and C stands for critical. Theta C equal to sine inverse of root of epsilon 1 by epsilon 2 or n1 by n2 or v2 by v1. Like that, we will be considering any one of these two relations. So critical angle theta C is given by here. The angle at which the total internal reflection takes place means that is the case transmitted wave fields and theta 2 to be considered as pi by 2 and incident wave making angle theta I is to be considered as theta c, then critical angle can be defined as the angle at which total internal reflection takes place is called as critical angle, or sometimes we may define as the angle at which incident wave is totally reflected at the interface of two different dielectric media is called as critical angle. Then generally it is represented with theta c equal to sine inverse of epsilon 1 by epsilon 2, where epsilon 1 and 2 are electric permittivities of both medium 1 and medium 2. When if the medium 1 is more denser than that of medium 2 case, the critical angle and total internal reflection takes place. Next, define Snell's law. So it is the law that gives the angles of reflection and refraction of a plane electromagnetic wave when the wave is incident on a boundary between two media. So there are two types of Snell's laws are there. Snell's law of reflection and Snell's law of refraction. So Snell's law of reflection means that is the case incident wave angle and reflected wave angle are same. Theta I is equal to theta r case. Snell's law of reflection occur, and sine theta t by sine theta I equal to beta 1 by beta 2, or whatever the relations we have considered for the, now we have considered here with respect to the phase changes as beta 1 and beta 2, and if you consider refractive indexes as n1 and n2, or velocities of both the medium v1 and v2, either of the directions we will be considering. Now depending upon that, the Snell's law gives us the angles of reflection and the refraction of a electromagnetic wave. So define Snell's law means it is the law that gives the angles of reflection and the refraction of a plane electromagnetic wave when the wave is incident on a boundary between two media. Right? So here Snell's law means depending upon his experiments, there are two cases are there, Snell's law of reflection and Snell's law of refraction. Whereas Snell's law of reflection case, that is theta I is equal to theta r, and for refraction case sine theta t by sine theta I equal to beta 1 by beta 2. That refraction case is said to be transmission, and that is replaced here theta t. Then define index of refraction. So it is equal to the ratio of velocity of propagation in free space to the velocity of propagation in the medium. Generally it is represented with n, and n is equal to c by v. Right? So index of refraction is represented with n, and it is equal to the ratio of velocity of propagation in free space to the velocity of propagation in the medium. So velocity of light in the free space medium is given by c, and the velocity of the propagation in the medium is given by v, and the index of refraction n can be represented as it is equal to the ratio of velocity of propagation in the free space to the velocity of the wave propagation in the particular medium, gives us index of refraction. Right? So in this we have learned the critical angle, Snell's law, and index of refraction. So critical angle can be defined as it is the angle at which the total internal reflection takes place is called as critical angle, and sometimes it may also defined as the angle at which incident wave is totally reflected at the interface of two different dielectric media is called as critical angle. It is represented with theta c, and it is given by sine inverse of epsilon 1 by epsilon 2. So to get the relation, we need to assume the medium 1 is more denser than that of the medium 2 case, that critical angle and total internal reflection takes place between two dielectric media. Then to define this Snell's law, we'll consider here two types of angles called reflection and refraction angles. So it is the law that gives us angles of reflection and refraction of a plane electromagnetic wave when the wave is incident on a boundary between two media. So depending upon his experiments, we'll be considering two cases as Snell's law of reflection, that is theta I equal to theta r, and according to Snell's law of refraction, that is sine theta t by sine theta I equal to beta 1 by beta 2. Then define index of refraction. So this is given by, it is the ratio of the velocity of the wave propagation in free space medium to the velocity of the wave propagation in the particular medium. That is given by here n is equal to c by v. Next is define loss tangent. To define this loss tangent, see, it is the ratio of the magnitude of conduction current density to the displacement current density of the medium. So generally it is considered to be as tan theta is equal to loss tangent. It is given by, it is the ratio of the magnitude of conduction current density, that is Jc, to the displacement current density Jd of that particular medium. If Jc is to be expressed as here sigma into E and dou d to be given by dou d bar by dou t. Generally dou d bar is equal to Jd is nothing but dou d by dou t. For a time varying fields, if that change dou by dou t is replaced with j omega and d can be expressed as in terms of epsilon and E, it is given by j omega epsilon into E bar. Then from this, tan theta is equal to sigma by j omega epsilon is given as loss tangent. See, loss tangent is the ratio of the magnitudes of conduction current densities to the displacement current density of that particular medium. Right? So from this we are going to define the loss angle also. That is represented as theta equal to tan inverse of sigma by omega epsilon. Depending upon that condition, whether the given medium is a type of conducting medium or dielectric medium, we will identify. Then define perpendicular and parallel polarization. So if the electric field component is perpendicular to the POI, if the electric field component is perpendicular to the plane of incidence, that is called as perpendicular polarization, and if it is parallel to the plane of incidence, then it is called as parallel polarization. Right? So perpendicular and parallel polarization means if the electric field component is perpendicular to the plane of incidence, and it is called as perpendicular polarization, and if the same electric field component is parallel to the plane of incidence, then it is called as parallel polarization. Perpendicular, and so from this we will be calculating two types of coefficients as tau parallel as well as tau perpendicular, and gamma parallel and gamma perpendicular. Tau and gamma are the two notations for reflection coefficient and transmission coefficients for the perpendicular as well as parallel polarizations. Right? In the parallel polarization case, we will be getting one of the angle called Brewster Angle. Okay? So to define this perpendicular and parallel polarization, we need to consider the electric field component with respect to the that one. If the electric field component is perpendicular to the plane of incidence and magnetic field intensity component is parallel to the plane of incidence, then the type of polarization is said to be perpendicular polarization. Similarly, if the electric field component is parallel to the plane of incidence and magnetic field component is perpendicular to the plane of incidence, that is the case, the polarization is said to be parallel polarization. Depending upon this, we will derive the two equations called transmission line coefficients and reflection coefficient of both perpendicular as well as parallel polarizations. Next, define Brewster angle. So, in the parallel polarization case, we'll be getting one of the angle called Brewster angle. So, generally, that angle is represented with theta, and Brewster is represented as here theta b. So, it is the sign of the, it is the angle of the incident wave at which no reflection takes place. That is, entire signal transmitted into the material. Means the angle, the Brewster angle can be defined as it is the angle at which no reflection takes place. Means whatever the incident wave touches or strikes the boundary, the complete wave is transmitted to the next medium. So entire signal is transmitted into the next material. That is called Brewster angle. There is a difference between critical angle and this Brewster angle. Whereas the critical angle case, the angle at which total internal reflection takes place, that is the case, there is no transmitted wave. But here in the Brewster angle case, the incident wave is completely transmitted to the next medium, there is no reflection wave, right? So theta c case, there is no reflection, and theta b case, there is no transmission. Sorry, there is no reflection here, and here there is no transmission coefficient. Okay, so that is the difference between critical angle and the Brewster angle. So critical angle is comes under normal incidence case, whereas Brewster angle occurs in the oblique incidence. So difference between normal incidence and oblique incidence also we have learned. When the incident wave touches normally to the boundary between two dielectric media, it is said to be normal incidence, and obliquely between two dielectric media means the angle which exists is exactly other than that of 90 degrees case. The type of incidence is said to be oblique incidence. Okay, so from this last tangent we have learned, and after that how to identify given one is a perpendicular type of polarization or parallel type polarization. Then after that we have learned Brewster angle. So to define this last tangent, we need to consider here two current densities, as one is conduction current density and the other one is displacement current density. So last tangent is the ratio of the magnitude of conduction current density to the displacement current density of that medium. Depending upon that, whether the given medium is a conduction medium or dielectric medium, depending upon that we will be identifying, depends on this loss tangent. From this loss tangent, we are going to measure the angle called loss angle, that is given by theta equal to tan inverse of sigma by omega epsilon. Then in order to identify this perpendicular and parallel polarization, it is completely depends upon electric field component and the magnetic field component. The electric field component is perpendicular to the plane of incidence, E is perpendicular to the plane of incident, and H is parallel to the plane of incidence case. The type of polarization is said to be perpendicular polarization. If the electric field component is parallel to the plane of incidence, E is parallel and H is perpendicular, then the type of polarization is said to be parallel polarization. In the parallel polarization case, we'll be getting one of the angle called Brewster angle, and it is defined or gives us an angle of incident wave at which there is no reflection takes place, and that is means the entire incident wave is transmitted into the material case. The angle is called as Brewster angle. Okay, so what we have learned in this particular lecture is the definitions and different terminologies which are exist in the uniform plane wave characteristics. So firstly we have learned what do you mean by uniform plane wave, how it is to be vary in different types of medium like free space medium, dielectric medium and conducting medium. Then we have learned three types of angles called, one is critical angle, loss angle and Brewster angle. Critical angle occurs in the normal incidence case and Brewster angle is occurring oblique incidence case, and loss angle is to be considered depending upon the conduction current density and convection current density. Sorry, displacement current density. Next, we have learned one of the angles called here critical angle and Brewster angle. So critical angle means it is the angle at which there is no critical angle is the angle at which the total reflection takes place, and whereas Brewster angle case, the angle of incident is completely transmitted to the next medium. There is no reflection in that, right? So these are the different definitions and terminologies which are used in the uniform plane wave characteristics in electromagnetic waves and transmission lines. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.